All right, so let me start with a review of what we did yesterday. So I first talked about the Komatsu duality in between Ising model and the link model. And Ising model is defined in a usual way, whereas the link model is defined in this way. And there is some constraint for each phase of the graph. And then I talked about generalized this like a duality between Ising model on a graph gamma and the link model on a dual graph to a bit more general model, which I called ZPQ model. And the duality is basically acts like exchange in P and Q. And the ZPQ model has two different degrees of freedom. One lives on the vertices of the graph, and the other lives on the links of the graph. And the one which lives on a vertex takes the values in ZP, and whereas the one which lives on a link takes value in ZQ. And the action is given in this way. And there is again some constraint, and there is also this Boltzmann factor for each link. And in the continuum limit, this is like an analog of, this part is the analog of del x del bar x of like a usual compact free boson. But the point is that if you want to discretize this kind of action, especially with the identification that x is compact, then you cannot just simply replace this derivative with like a discrete, with difference, because if you consider a discretized lattice on which this compact boson lives, then sometimes like when you go from one lattice to the next lattice, then actually the x can wind around this circle several times, and this is basically taken into account by this extra factor.
This duality is valid for any.
Right, and this duality, the point is that this duality is valid in any genus. And that is actually important because today I'm going to talk about generalization of this duality on random lattice. Yes?
So, you said this is a discrete version of T-duality and so on.
Yes.
I was wondering whether there is some kind of a fewer theory or something where you can actually realize this explicitly.
Creeper-Sari, you mean you are talking about something like deconstruction?
Yeah, or even like, like if I can, let's say, have some brane construction and make this statement precise, where I can arrange the branes in some.
I see.
Like some, let's say, D-branes.
Right.
Questions and
yeah.
get some integrated.
Right. Actually, so what I'm going to talk about today is a little bit in that direction. I'm going to make several comments related to that, but I don't quite know like how to precisely realize this model. And one peculiarity of this model is that there is some cutoff in the winding number, because the M is like winding number and then it's cut off at ZQ. So I don't know how to really precisely like realize that in real string theory, but I'm going to make comments related to that today.
That's a bit like now before.
Right, right.
When you have
yeah, it's up to some, yes. Mm-hmm. I see. Okay, yeah, maybe it's good to discuss later. Yeah, but okay, let me just first talk about this topic. So now what I want to do is to generalize this generalized Komatsu duality to random lattice. But before doing that, I first need to state what is the Ising model on the random lattice, or more precisely, dynamical random lattice. So let me just first write down the action. And so the action, or the partition function, is now given by some integral of matrices. So you have two n times n matrices, M1 and M2, and then you have some action, S of M, and S of M consists of kinetic term and interaction term. Okay? And the kinetic term is given by this expression. So let me just first write it down and explain what it means. So you have trace of M1 square plus M2 square minus 2 times e to minus 2 beta M1, M2. And the interaction term is, well, you have some coupling constant, and then I just put some random potential, like a polynomial potential in M, M1, and M2. Okay? So this is the action. So, and V is at the moment like an arbitrarily polynomial. So at this point, like it's probably a bit unclear why this is Ising model, but this you can understand by considering the Feynman rule of this matrix model. Yes, this is, yeah, Hermitian matrices, yes. Okay, so let me just write down the Feynman rule. So first of all, there is a propagator which comes from this quadratic term, because this is a kinetic term. And basically, the propagator can be read off by inverting this quadratic term. And now, because everything is matrices, so basically the propagator, you can like write it in terms of usual double line notation of large N theory. But you need to remember that you have two matrices. So the propagator have there are 4 different kinds of propagator. The first one is the one which connects 1 and 1, and the second one which is the one which connects 2 and 2. And because of the symmetry, these two propagators are the same. And then if you compute it by using this action, then you get e to beta. On the other hand, there are also other 2 propagators which connects 1 and 2. Yeah, there are too many double line, but this is equal. And then you also have like the one which connects, yeah, 2 and 1, and that is equal to e to minus beta. So this is already a bit like Ising model. So if you view 1 as, for example, upspin and 2 as downspin, then this is basically telling you that if 1 and 1 are connected, up and up are connected, then you get e to beta. But if up and down are connected, you get e to minus beta. And that is the analog of this factor that you got in the Ising model. But of course, this action doesn't just have this kinetic term, but it also has the interaction term. And the interaction term in the double line notation is something like this. So you have like interaction term of Vm1 and Vm2. And in particular, if you just consider some quartic interaction term, then in the double line notation, you get something like this. So, which is the vertex of double line, which is of this form. And if you construct some like a Feynman diagram or graph using these Feynman rules, then the typical graph that you would get is something like this. So you have something coming in, and there is a vertex, and then there are lines coming out. And then, so let's just connect it in this way. So this is one part of the diagram that you get by applying this Feynman rule. And then you basically need to there are like two choices for each vertices, which is like 1 or 2, or 1 or 2. And so topologically, this is the same as like the structure of the graph is the same as this one, right? And then what we need to do is to put 1 or 2 for each vertices. And depending on 1 or 2, you put a different Boltzmann factor. And this makes it clear that this is a kind of like a Ising model, but defined on a random graph, because you can have like many different graphs coming from applying these Feynman rules. So this model was first introduced by Kazakov in 1989, and then it was used to give a non-perturbative definition of the Ising model coupled to two-dimensional gravity. But I'm not going to talk about that very much today. Instead, what I'm going to ask today is that, so this model defines you some like Ising model defined on a random lattice, but then can you define, or is there any Kramers-Wanier duality acting on this model? So this is the question that I want to address today. But in order to address this question, I should point out that it's very important to have a Kramers-Wanier duality in arbitrary genus Riemann surface, because if you apply this Feynman rule, then you typically get not only sphere worldsheet, but you typically get like a higher genus, graphs that are drawn on higher genus surfaces. So that's why yesterday I talked a lot about the generalization of the Kramers-Wanier duality that applies also to the higher genus Riemann surfaces. Yeah, yeah. So it's not super obvious. You just need to. Yeah, you need to invert it. So that's the point. Okay, so let me first state the statement of the duality. So there is a Kramers-Wanier duality acting on this model, but as in the case of the fixed lattice, the Kramers-Wanier dual of this model is actually not the same model, but it's a different model. So the statement is that, so let's consider random lattice Ising model with the same kinetic term, but now I consider very particular potential term, interaction term, which is given in this form. Trace log 1 minus g m1 plus trace log 1 minus g m2. And so this looks a bit weird, but you can just expand the log, and then you see that you have like many powers of m1s and m2s. So this is just a particular case of this potential. And in the dual model, so the analog of the link model, now defined on a random lattice, is given by some kinetic term, which I write later, plus, again, there is trace log with potential interaction term. But now there is one big difference. So now you have only one matrix, a single matrix. Instead of having two matrices, but this matrix is actually 2n times 2n Hermitian matrix. Okay, yeah, so I'm going to explain why this model is really like a random lattice link model. So it's really like a generalization of what I talked about yesterday. So, but to do that, I need to, before doing that, let me just write down the kinetic term, which is a little bit complicated. So you have something similar to what I wrote over there. But now, the kinetic term consists of two terms. The first term is the usual one, and there is yet another one, which is omega m twiddle, omega m twiddle. And let's see, right, so this is the kinetic term. Yes, yeah. I was expecting the comment. and let me just write what omega is. So let's keep this part. So let's just keep this part. This is the Ising model action. But yeah, in general, this kind of action, yes, but let me just first write what omega is. So omega here, so because this is 2n times 2n matrix, I can just decompose the indices into 2 and n. And if you do so, the omega has this form, and this small omega is 2 by 2 matrix. And the important property of this small omega is that trace of omega is 0, and 1 over 2 of trace of omega square is 1. And there are many ways to realize this kind of matrices. So the simplest one, so basically like any Pauli matrices will do the job. So the two simple choices are like this, and it doesn't matter which choice you take. So this is a definition of omega, but now let me give you a couple of comments. So this kind of matrix model with this weird kinetic term was first discussed in the paper by Das, Dar, and Sen Gupta, and Spenta. And in that paper, so this paper is usually regarded as a paper in which they introduce the double trace deformation. But there is also the first part of that paper, and in that first part, they discussed this model. And because this model was hard, they instead discussed the double trace matrix model. But like what I'm going to talk about today is a particular case of what they discussed. And let me see. So yeah, there was also subsequent development by Kazakov and his company, and in which they developed a kind of like a method to analyze this kind of matrix model. And this kind of matrix model is often called like a dually weighted model in that context. But I will make more comments probably later. And so this is the definition of the model. And first of all, okay, so another related comment is that the claim is that this model is dual to this two-matrix model. So this also gives you an idea that this model, although it looks complicated, can be solvable because this two-matrix model is solvable. And another comment I should make is that why this model, why the duality between the two is the Kramers-Wany duality. And you can see that by considering again, the Feynman rules of this dual model. So let me just try to understand it. So because the kinetic term is a bit complicated, now it's even more difficult to understand what is the propagator or read off the propagator from the action, but you can still do it. And the result is as follows. So now, because matrix twiddle, M twiddle is 2n times 2n, I split the indices into two parts, like a 2 by 2 part and n by n part. So I write the matrix indices in this way, and A takes value of 1 or 2, and I takes value from 1 to n. So this is the definition of the model. So sorry, this is the way to express the matrix indices. And then what I'm going to do is to read off the propagator. So now the propagator has many indices. And if you read off the propagator starting from this action, that action, you discover that there is a piece for the UN piece. The propagator is just the usual delta function propagator. And then there is this factor for the 2 by 2 matrix, but in addition, there is this extra factor, omega BC. So this is the propagator. And if I were to introduce some double line notation, because this like a UN part is the usual one, I would again write the usual double line propagator to take into account the UN piece of the indices. But in addition, I need to remember that each matrices are decorated by like these Z2 indices. So I need to put some extra indices, like which takes value 1 and 2. And furthermore, because the propagator consists of two parts, I would introduce two different kinds of propagator. And the one is the usual one, and the other is this one, which accounts for this omega piece. So this is already a bit like link model, because you can see that there are actually two different kinds of links. And if you draw a graph using this, then, okay, again maybe I shouldn't have erased, but again you have like this kind of double line graphs. And then now there are like different choices of the propagator. So for example, I can try to choose this yellow propagator for this and then use white propagators for the other ones. But it turns out this particular graph is actually 0. And why is it so? And it is so because if I choose this yellow part here, then I need to multiply omega matrix for this propagator, for the Z2 propagator. And whereas I multiply 1 here and 1 here and 1 here. And if you sum all the indices, then from this face, you get trace of omega. But because I choose a particular omega, which satisfies trace of omega is 0, you can conclude that actually this diagram vanishes. And the only non-zero diagrams are the one which contains even number of yellow lines for each faces. So basically, this is saying that for each face, so number of this yellow propagator, which must be even. And this is precisely analog of delta 2 that I introduced yesterday, which appear in the definition of Z12 model, and which is basically link model. So in this way, we can see that this model is really the random geometry generalization of the link model. Okay. So okay, so let me give you another comment. So let's just keep this part of the kinetic term. So the comment is that if M twiddle takes is a diagonal matrix where this is n and this is n, and if you were allowed to neglect off diagonal parts, and then if you further take omega to be 0, 1, 1, 0, which is just a 0, 1, 1, 0 times this, then this kinetic term simplifies, and then it basically takes a similar form as the kinetic term of the random lattice Ising model. But so in some sense, this link model or random lattice link model is similar to the random lattice Ising model. But of course, it's not the same, because if you really want to integrate over the matrix M twiddle, you also need to take into account off diagonal modes. So this is what actually distinguishes the Ising model and the link model. And you can actually show that if you just consider the a large n answer, these two models give basically the same answer. So this is the analog of the statement that if you just consider the spherical lattice, then the link model and Ising model are basically the same. But if you consider higher genus surfaces, then there are differences basically coming from the off-diagonal modes.
No, but you're saying the link model, the full model is the same even on higher genus.
Right. So okay. So the statement is that you need to distinguish the two. So there is a duality between link model and Ising model, but the point is the link model is not the same as Ising model. Yeah. So that's what I was saying.
Only on the sphere, the link model
is really the same as Ising model. Yeah. So right. I forgot to mention that. So the claim is that. So let me just write down the claim. So claim is that Z Ising at temperature beta is Z. So let's just Zm twiddle at temperature beta twiddle. And the relation between beta and beta twiddle is precisely given by the Kramers 1A duality. And this is correct at finite n. So this is the claim about the duality.
A reference for this duality.
Sorry?
A reference.
Actually, that's the same paper. So also in that paper, this is also discussed. So it's the paper by Yone and his collaborators. Okay, so another comment I can make is that, which is a bit related to the relation to the real string theory, is that, so this is more like a comment to people that knows the stuff, but this is a kind of like a discrete version of T-duality in gauge theory. Proposed by, or discussed mainly by, Washington Taylor. So in his version of T-duality, so he basically proposed some duality between gauge theory with group m times infinity and the d plus one dimensional theory living on with gauge group So this is discussed by Taylor around 1996. And in some sense, what we have here is the analog of that. So, and the difference here is that now this infinity is replaced by 2. So this link model is just like is a zero-dimensional matrix model with gauge group 2 times n. And the other one, with the Ising model, is made up of 2 matrices. And but you can view these 2 matrices as like a very simple, like a discretized extra dimension. So in this sense, this is the analog of the T-duality for the gauge theory discussed by Taylor. Okay. So this was one comment. All right, so now I'm going to...
What about either of these models? How did the partition function come?
How to show the duality?
No, what do these models look like from a face? Are they faces? What happens in that?
You mean this model? So, okay. Eigenvalues. So people generally don't, well, there is a way to study this model first, developed by Kazakov startup here in winter, but that doesn't use eigenvalues. Like that uses character expansions, and that's kind of a bit complicated. And on the other hand, on this Ising model side, there is a way to solve the model. So the Ising model is made out of 2 matrices, and then you have M1 times M2. But you can actually integrate out this. So typically, the way to solve the matrix model is to write it, decompose it into a eigenvalue and the UN group, and then integrate out UN group first. And so it looks a bit more complicated, but still you can actually do the integrating out, because there is yes, Harris-Chandra-Isaacson-Zuber formula, which allows you to do this kind of integrals. Yeah, to matrix integral.
What is this for?
Harris-Chandra-Isaacson-Zuber. Yeah, and essentially that gives you. Well, I'm not sure. Yeah, that gives you character. Determinant e to something like AI bj over delta of AI delta of bj. And AI is the eigenvalue of M1, and bj is the eigenvalue of M2. So basically, you can reduce everything into eigenvalues.
And does it have
that's studied in the context of an Ising model.
So who has studied? What is a good reference for this?
Noether was the first. Noether studied the 2 studies.
Okay, yeah.
Zuber review article, I think.
Yeah. Yeah.
If you're interested in phase transition, there's a paper by Gross and Migdal, Kazakov.
Yeah.
The phases. Not Gross and Migdal look for the existence of
Right, yeah, so this comes from a brain intuition, yeah. Okay. So
I can sort of see where you go. I mean, you think that the log potential Is there a specific reason? I just want to hear what you
Okay.
feel is the specific reason to choose the
Right. So actually, this is just for the convenience of the presentation. So if you take the log potential, the potential part becomes self-dual. Like you have log here and you have log here. But yeah, if you choose other potential, you need to do something like a Fourier transformation. Yeah, the potential part gets modified.
Universal actually, you can just
Yeah.
the logs.
Yeah. Yeah, you can generalize to more general potentials. But yeah, the way to generalize to general potential is just like put many logs and then like tune the coefficient so that you get different potential power, different powers. All right, so yeah, so let me now just try to prove it. And again, so the proof consists of 4 steps. And so integrating in, and out. And this is precisely the point where there is some connection with open-closed-open triality that we just discussed a few years ago. And so in the step 1, so what I'm going to do is to take the Ising model, random graph Ising model, and then convert it into the random graph link model. And the step 1, so in the Ising model, I chose the specific potential, which is the log potential. And if you put it in the exponent, then of course, using the usual formula, this gives you determinant to the power n, right? And because it's given by some like 1 over determinant, it's very natural to introduce some express it as an integral of bosons, like a bosonic degrees of freedom, where A runs from 1 to and I runs from 1 to n, and then d phi ai dagger, d phi ai, and then you put exponential of a and I, and phi ai dagger, and 1 minus g ma phi ai. And let me just briefly explain what they mean. So these phi ai, so individual this phi ai is the fundamental of un. So there is actually a secret index that I didn't write, and that index gets contracted with the indices for this matrix. And on the other hand, this is similarly anti-fundamental of UN. So basically, phi and phi dagger has 3 different kinds of indices, and one is this like a Z2 valued index, and the other is this index which takes value from 1 to n. But they are basically like more like a flavor index. And in addition to that, there is like a gauge index, which I didn't write. I shouldn't use the same. But because I have too many indices, so I should probably like invent some better notation. So I'm going to express this part in this way. So I just use like a quantum mechanics like notation. And this basically means that you are taking inner product in UN indices, like a gauge index. And then you have some flavor index as well.
The log potential is very important.
Yeah, here it's important. And actually, like when you try to generalize it, you start from log and then put many logs and then get different potential. Yeah. All right, so this is step 1, right? And then, so now the step 2 is, so in the step 1, I integrated in extra variable, and in the step 2, I integrate out original variable. But before doing that, let's just rewrite M1 as square root of 1 plus u plus v, and M2 square root of 1 plus e to 2 beta u minus v. This is just for convenience. So I introduced like a new n times n matrices u and v. And after this rewriting, kinetic term becomes a bit simpler because there is now no coupling between v and u. And furthermore, you see that beta twiddle emerges. Yes, v squared. Yes, thank you. Emerges in this rewriting. But on the other hand, interaction term becomes a bit more complicated. And so the interaction term the interaction term gets more, now contains this phi degrees of freedom. And interaction term is now given by this expression. So you have phi AI, which basically comes from this one part in this 1 minus g times m. And then, in addition, there is a coupling between phi and u and v, and that is given by this expression, phi AI, u phi AI, plus phi AI, v phi AI. Sorry. So this is not correct. I have this here. And the index b is summed. And this is precisely, in this particular derivation, this is 1, 0, 0, minus 1. So this is what you get. And basically the reason why you get some like a weird factor omega is that now M2 is u, so u minus v. So u basically couples like uniformly to both phi 1 and phi 2, but v changes sign between like a phi 1 and phi 2. And one way to incorporate that is to multiply this matrix here. Is this point clear? And g twiddle is something like a 1 plus e beta g. Okay. Now, so to proceed, so this is the kinetic term. Sorry, this is the interaction term. And to proceed, I pick this. I slightly rewrite this part. So this part you can also write it in this way, because like these indices are completely summed, AI. So you can rewrite it in this way. So u times phi AI this is just a different way of expressing the overlap of this quantum mechanical system. So this is just trivial rewriting. Okay. And then I'm going to denote this O and denote this operator O hat. So with this, I can now integrate out original matrix U and V using this kinetic term and this coupling. And now, so this is very easy because U only appears at most quadratically and V also only appears at most quadratically. So you can basically integrate out U and V by completing the square. And if you want to complete a square, then basically what you need to do is to rewrite this term in this way. So the full action can be expressed in this way. So on the other hand, you have O hat. So you basically shift U and V to absorb this linear term, and then subtract this extra part. And then integrate out shifted fields. So this is how you do the computation. And as a result, if you integrate out, then these parts are gone, these parts are gone. So you are just left with like O square or O hat square. And so what is this O square? So this O square, if you write it explicitly, then the trace of O square, then it's a trace sum over A, B, I, J, and trace of phi AI, phi AI, phi Bj. So this is just coming from the definition of operator O. And then you can, of course, rewrite it by putting this part to this part. And the final answer is given by this. You have sum and okay. So this is the final expression for traceable square that you get after integrating out U and V. And if you look at this final expression, then you see that now this definition of O square, this expression of O square can be interpreted as some kind of multiplication of the matrices. So more precisely, let's define this inner product and let's write this inner product in this way and regard it as the matrix. Then precisely what is happening is that you are just multiplying these matrices and taking the trace. So now this object becomes. Yes.
If you have an imagery, some shifting to show that.
Sorry. Yeah, so these are Hermitian actually. Yeah. Yeah, because it's just a redefinition. Yeah. Yeah, it's just because of bad notation. Yeah, sorry. Yeah. So yeah, so because it's Hermitian matrix, you can just do it. And then the point is that final answer can be expressed in this way. And then this you can view it as some like a matrix multiplication. So trace of O squared now becomes trace of phi squared. But I should clarify one point. So both are given by trace of something square, but the meaning of the trace is different. So here I was just taking a trace in U and gauge indices. But now here I'm taking a trace in 2n times 2n flavor indices. So in this way, you don't see the original U and gauge indices, and then instead you are left with the flavor indices. Now, you can basically do the same for the trace of O hat square.
It's a matrix of full rank.
Okay, so this is, so far this is just one way of like a notation. And in the next step, I'm really like introducing the real matrices. So this is just a way of like compactly writing the final answer. So, and if I use the same notation, then I get this for O hat square, and now this omega is the one which will appear in the final expression for the link model. But so far it is not really a link model because as pointed out, these are not really, like these phi's are not really matrices, but it's instead bilinear of some vector like degrees of freedom, phi ai and phi bj. So in this way, I got some action which looks like quadratic action of big matrix phi, but it's actually not, because this phi is bilinear of the fundamental field. So this is the action that we got, but you need to remember that this phi square, although it looks like a quadratic, and this also looks like a quadratic, but it's actually quartic in the original variable phi. Okay. So, but it's not so bad, because if you have something quartic in some vector degrees of freedom, then we basically know how to solve it. And now the steps 3 is do the Hubbard-Stratonovich trick. So basically, what I'm going to do is that take this action and then integrate in. Now, a real 2n times 2n matrices, and so that so you have some kinetic term for m twiddle, and so that phi only appears linearly, and I choose the kinetic term so that after this is bilinear, sorry, this is quadratic and m twiddle, and I choose the kinetic term so that like after integrating out m twiddle, I get back to the original action. This is always possible. I'm not going to write down the explicit expression, but it's possible. And once you do that, then it now becomes trivial to integrate out phi's, because phi only appears, so this is the quadratic in phi. So then, finally, in the step 4, I can just integrate out phi. And that basically gives you the expected link model. And I should emphasize that when you integrate out phi, because phi is the fundamental of U and H degrees of freedom, there are actually like n copies of phi's. So that's why you naturally get n times trace log. So this comes from the determinant. All right, so this basically completes the proof of the equivalence between the link model and the Ising model. But okay, so this 4-step of procedure was a bit complicated, looks a bit complicated, and it's not very intuitive, but there is a very nice graphical interpretation of each step of these procedures, which is basically pointed out by Rajesh in a different context. And this graphical interpretation also makes it clear that this is really a Kramers-Wanier duality in which you map a model on an original graph to a model on a dual lattice. So let's try to understand that. So originally, I had some Ising model on a random lattice. And in the Ising model, there is a vertices, and for each vertex, you can choose one and two indices because there are two different kinds of matrices. And right, so and what we did is basically to, so in the step one, I introduced extra degrees of freedom phi and rewrote the vertex, which is trislog part, into a quadratic action in phi. So this is basically, in the graphical notation, this is basically like adding some extra line here, dashed line, which takes value in 1 and 2. And after doing so, you see that there is some object running here, which has the fundamental of UN and anti-fundamental of UN. And then that couples in a way like a phi dagger, and M in the original metric. So this you get phi dagger, M phi. So this is precisely what we did by integrating in. And in the next step, I integrated out U and V. And so when you do so let's just take some particular graph that arises from this. So let's take this graph and then integrate out original U and V field. So that basically kills this propagator part, and that gives you quartic action in phi. So this is precisely the quartic action that I got here. So this is the steps 2 and 3, and then finally at the next step I integrated in extra variables. Basically I did the Hubbard-Stratton-Witt trick, and in the graph this basically amounts to resolving this quartic vertex, but now in a different way. And once you do that, you can just like integrate out phi's. So this is the step. Integrating out phi. So this is the step 4. But one important point that I want to emphasize is that if you superpose the graph that you obtain here with the graph you started with, then you see that in the original graph, the propagator runs in this direction, but in the final graph, the propagator runs in this direction. So this is precisely graph and dual graph relation, or lattice and dual lattice relation. So in this way, you can convince yourself that this is indeed the random lattice version of the Kramers-Wanier duality that I discussed yesterday. So, all right, so far so good.
Any idea about critical phenomena here? I mean,
Well, this is basically the Ising model, so
you tune to the multiplication
yeah.
points. So that's how there'll be a PQ generalization.
Yeah.
So you get plots.
Right. Yeah.
if you take more, Douglas had introduced a model with his. So it's like this is like coupling minimal model to 2D gravity
Mm-hmm.
for central charge half.
Mm-hmm. Yes, yes.
But then one can generalize those to,
Right.
and all of those most probably you may be able to.
Right. That's true. Yeah. Yeah. Right.
So
Yeah.
couple all minimal models.
Yeah. So so indeed, like the PQ I introduced yesterday might be somehow related to PQ in the minimal model, but
no, it is not the PQ again. Like you said, that
Yeah.
will be the false model. You need
Right.
Q matrices.
Right. Yeah.
Thing, and then you will have
Okay.
P comma Q minimum. You have to go to the Qth critical point of
Yeah.
the
Yeah.
and so on. Yeah.
Yeah.
So there's a potential you have to tune to go to the
Right.
other
Right.
one.
Right.
Usually in such models, we don't use the logarithm.
Right.
But if you use the logarithm potential, then you're tricky
Yeah. Yeah.
to just redo the whole thing.
Yeah.
But for more than 2 matrices.
Yeah.
Right.
Yeah. That's true. Yeah.
And then you fine tune the coefficients of the
Right.
log, and then you get out the different,
Right. Right. Yeah.
points. Yeah.
Yeah. So I think that's kind of interesting direction to explore. But yeah, actually, this is not my trick, but this is their trick, but because it's not about my work. So. But anyhow, but I think nobody really studied that kind of extension. So it's I do agree.
The extensions of this is not known. If that's
Sorry, which peak? I talked about yesterday. Yeah, you can also write it down. Yeah.
With there, your small omega would be some pth root of unity.
Yes. Yes. So it's going to be something like that.
So all lower products are all 0, traces are 0.
Right. Right.
Except the pth.
Yes.
Power.
Yes. Yes. Exactly. Okay. So. Right. Let's see. Yeah. Now I don't know what to talk about the rest of the time, but.
We can start. Maybe
Yeah.
we can go for 15-20 minutes today. I think there's no sharp cutoff at points.
Okay. Sorry. What did you propose? Like go.
Maybe 15-20 minutes. If there's some topic you think, because I guess you're a little behind your schedule.
That's true. Yeah, but of course, I don't need to talk about everything that I prepare, but.
Get down to your work.
That's true. Yeah. So far, I have been discussing other people's work. All right. So. Yeah.
Answer. So here the statement is that at the level of graphs.
Yes.
You have some genus graph.
Mm-hmm.
This doesn't convert the genus.
No. It's really like T-duality. So.
It converts it into dual.
Right.
Okay. And it also it is like T-duality also in the sense that.
Yeah.
And it is true at even finite n.
Yes. Yes. Yeah.
And the statement for the PQ is the statement that you can write down some kind of a link model.
Yes. Yes. Yes.
And then it gets exchanged.
Right. Exactly. Yeah.
So, what do we know about what do we know about the larger limits of such theories?
Actually, for general PQ, it's hard to solve. So this one, you can solve it because it's like a 2, 1 or 1, 2. So if you go to one frame, it's just like a multi-matrix model, which you already know how to solve. But for general one, it's hard. But I think, and that's basically the point where they stopped. But I think now there are a little bit more technology because thanks to Kazakov and his company, because some of these a trace AM type models can be solved using the new technology of character expansion. So I think some of them can be solved, but like the most general ones are still hard to solve, I think.
And and do we know how such theories are realized? Say within there's intuitive realization for this.
It's not well explored, I think.
At the critical, only non-critical strings that you get
right.
probably when you fine tune.
Yeah.
So, I mean, it's related to the thing that if you introduce more than two matrices, so let's say Q matrices, and type of potential that you have, you can write down a dualized version of that. Now, I mean, except for C equal to half, there's this whole infinite series of critical points for C less than 1. I mean, nobody had an idea of what a dual representation would be without random graphs, actually. So this is a very interesting result. Actually,
I see.
That, I mean, for any C you choose, that depends upon the number of matrices you use, then there is a dual representation like this.
Yeah.
The steps all go through, of course.
Right. So when you say dual, it's really like a dual in this sense. I see.
No, but I think there is the analog. I think that was studied at that time as this generalized Kontsevich models that some Russians they studied.
I see.
Morozov and other people, they had similar. It was never, people used mainly the original multi-matrix models, I think. But towards that back end, I think people, after Kontsevich introduced this, there are other generalized Kontsevich models that the Russians studied,
which are actually related
you can
to
go to
this
the
question
QN's matrix model, I mean QN's critical point. And the Kontsevich model is for the 2, 1. But
T-dual models, they also have T-dual models.
This is a similar kind of process, but you are tuning to criticality.
So you have equations for the external sources and
design
systems and all that.
Exactly.
Okay.
Whatever that.
This is good. In one blackboard talk, you can see the duality actually of such a complicated.
Okay. All right. So let me then now make one extra comment. So far I only discussed the partition function, they also only discussed the partition function, but it's probably also, you can also, of course, like easily generalize this to the correlators. And for instance, you can insert something like a trace, something like single trace operator in the Ising model side. And then with this insertion of the Ising model, with this insertion of single trace operator, you can try to keep track of the duality. And so in terms of the random graph, this insertion basically inserts some fixed, so basically this inserts some fixed vertex of like a 1, 2, 1, 2, 2 inside the random graph. And if I were to give some Ising model interpretation, this is a bit like inserting some fixed Ising spin chain inside random graph. And then you can try to follow how the duality goes, but and roughly speaking, at large n, at least at large n, this single trace operator gets mapped to again a single trace operator. But now I have a single matrix M, but now there are like a different kinds of operator in which you insert some omegas here. So if you follow the procedure, then you can see that this kind of single trace operator gets mapped to this kind of single trace operator, at least in the large N. I'm not going to present this now because later I'm going to do something similar in the context of N equals 4 super M mills. But you can also do it in this model. All right, so that was one comment that I wanted to make. And yeah, I don't know. This is actually a good point to stop, but yeah.
So, I mean, that's up to you.
Yeah.
Right?
Yeah, maybe we can just, yeah, stop. But let me just say like what I'm going to talk about next. So tomorrow I'm going to change the topic a little bit, and I'm going to talk about baryons and determinant in large N, and then try to see some kind of similar structure somehow emerges in that context as well. So, okay, maybe that's it for today.